Alrighty, recording started. I will give everyone the benefit of the doubt and assume they are absurdly late. So, just gonna. Oh, there's one student. Just gonna let this minute finish, and then we'll start the tutorial. Alrighty, it's 8:30. Let's go ahead and get started. So, the binary search tree. The binary search tree is a fun little data structure because it is, well, it's entirely recursively defined. And recursion with object-oriented isn't something you typically see except for data structures like these. So I'm going to quickly go over what a binary search tree is. I have the rules of a binary search tree here, but I want to genuinely know, like, I want to go over a proper example to make it clear of what's happening. So I've got my tablet here, and I'm gonna take an array of data. Typically when you see arrays, you see them as like horizontal squares like this. And I'm gonna turn it into a binary search tree by inserting every item. So you can actually see what happens with a binary search tree. What's the thinking? What's the logic? So a binary search tree is comprised of these squares. They're called nodes. And each node can have a left child, in which is either another node or it would be nothing, and can have a right child, in which is another node or can have nothing. These children are determined based off of the result of some sort of function. A function that takes in the root node and either the left child or the right child. Basically, it takes in some sort of root and some sort of child. And what it should output is a Boolean. It should either be true or false. Now, for the sake of simplicity, we're going to assume that the function in the examples we're going to be looking at is going to be the function greater than. Basically, what's going to determine if we go left or right is we're going to ask, is root, or I should say less than, is root less than child? If root is less than child, we are going to go right. And if root is not less than child, we are going to go left. So that's what's going to determine how we traverse our binary tree. So let's take this array of data, put it into the tree, so you can see exactly what happens. We start with the number 10. The number 10 is going to become our root because we have nothing in the tree. We then go 11. Is 11 less than 10? No. So 11 has to go right. Then we stop. 4. Is 4 less than 10? Yes. So we put 4 here and we stop. 7. Is 7 less than 10? Yes. However, this child node is no longer empty. So is 7 less than 4? No. So we have to go right and we put 7 there. You repeat the actions. So 3 less than, go left. 2 less than, less than, less than. We keep going left. 12 greater, greater. 6 less than, greater, less than. 5 less than, greater, less than, less than. 8 less than, greater, greater. And I'm just going to plug in the rest since you guys probably see where this is going. And that's a binary search tree. Everything to the left of some sort of root is going to be less than that root. Everything to the right of some sort of root is going to be greater than that root. The benefit of trees like this is it is faster to search a tree than it is to search an array. So if I were to ask you, does the array at the top contain 14? What you would have to do, and I'm just going to pick a different color, let's go yellow, is 10 14? No. So we mark 10 as looked at. Is 11 14? No. Is 4 14? No. 7 3 2 12 6 5 8 14. We found it. We looked at 1 2 3 4 5 6 7 8 9 10 11 items to find 14. Now let's look at the tree. Is 10 14? No. 14 is greater. Is 11 14? No. 14 is greater. Is 12 14? No. 14 is greater. Is 14 14? Yes. We looked at 4 items because we always can say 14 should be to the right of the parent nodes. It is significantly faster to find target items in a tree than it is in an array in the average case. So that's the benefits of a binary tree. However, we need to code those benefits. We need to take the logic and put it to actual good use. So let's take a look-see. I have 2 people, so if you guys have questions, you can either unmute whenever you need, or you can just throw it in the chat. I'm gonna keep frequently checking the screen where I have my chat, so I can you can see that. So, binary search tree, just going through the rules, recursively defined as this data structure is. Every node has a root, a left, and a right. If the value is already in the tree, you don't add it. So we're going to take a look at the bin tree class, and we're going to ask, well, what is a binary tree? Well, it's all of those squares. It's all of those nodes. So what we're going to need is some sort of self.root, and we're going to need some sort of root data. So that's going to be our root number. Then we're going to need some sort of self.left, which by default is empty. By default, it's none. And we're going to need a self.right, which again, by default isn't right, sorry, it would be none. Now, optionally speaking, you could also define your predicate function, the less than. So if I wanted, I could do predicate takes in, I'm just going to make a lambda function, takes in some sort of root node and some sort of child node, and returns if root is less than child. You can always do this. I'm not going to do it that way. That would be a bonus if you guys wanted to do it that way. So let's code that insert logic, because we have to one by one insert all of the items into the tree. We have to insert 10, then 11, then 4, then 7, then 3, then 2, then 12, then etc., etc. So what is the insert logic? Well, if self.root is equivalent to none, we should probably just set self.root to be the value, right? Because no matter how you're looking at it, if you're inserting something into an empty square, the square is empty. You should be absolutely 100% allowed to do that. That's the easy case. What if self.root, however, is not none? Well, in this specific situation, we have to then ask, is the value we're inserting greater than self.left? Because, or not self.left, sorry, self.root. I done goofed. Because if the value we're inserting is larger than the root, we should go right. And I really should, for consistency, have done less than, not greater than, because that's what I was teaching you guys in the example. So if self.root is smaller than the value I'm inserting, I need to insert that value into the right side. However, if self.root is strictly greater than the value, not root, I should go left. What happens if self.root equals value? Well, nothing happens. You could think of it as this first case. If self.root is equivalent to value, then you're just setting self.root equal to value. Nothing changes. So those are my four cases. I either am inserting into an empty square, found a square with the exact same value, found a square that is smaller than the value I'm inserting, or found a square bigger than the value I'm inserting. What goes here? What goes here and what goes here? Because these are the two lines of code that really determine the insert logic. And it would make sense if I want to go right to just self.right insert value. If this tree is recursively defined, you could imagine every subnode as being its own binary tree. So if I want to use the insert function recursively, I need to make sure that when values do get inserted, that they are some sort of binary tree. So I would actually do bin tree root, not root, value. This gives me access to recursion logic. By having every root be a binary tree with the value of root, it has its own left, it has its own right, it has its own insert, it has its own search, etc., etc. So if I just run this code and print it, none type has no object. Ah, yes, none type has no object insert because self.right could still be none. I have to actually, if self.right equals none, then I have to do this. I have to make it a binary tree. If it is a binary tree, I just call insert on it. That was my bad. So if my root needs to go right, check if self.right is empty. If self.right is empty, then what I'm going to do is I'm going to make a binary tree in that spot, and I'm going to put the value in it. Else, I'm going to recursively call the insert function and keep going down the tree. And the logic applies for left as well. String returned none type. Sorry, what? That shouldn't be happening. Well, welcome to debugging with Mark. Let's see if we can figure out what's going on. So I made a print function just so we could keep printing the tree because it would be easier to see the tree. And apparently the logic of that print function is flawed. So I have to find out what is returning, because I'm casting all of these strings, which means that nothing should be an issue. So eventually, if I follow the tree, string dot left then has its own string dot left, has its own string dot left, has its own string dot left, has its own string dot right. But this should only happen if self dot right does not equal none. Maybe it's something to do with my print or inserting logic. It's really early in the morning, so I'm just let's take a look at my insert function and see if I can identify what's going on. If any of you guys see the issue, feel free to call me out. Let's see if I can find in my example. Self.root equals root, self.left equals none, self.right equals none. Oh, if self.root equals none. No, this very much is. I wonder if it's because I'm not returning. I shouldn't have to return anything for this. Because eventually the recursion will just stop. Okay, let's try just something. If self.root, because the root is always defined, which means you should never have a moment where self.root equals none. So let's try that. Self.root is less than value. If self.right is none, set it to be a binary tree with that value as the root. Else self.right dot insert value. Then let's do just a generic else statement. Left, if self.left is none, set to be a binary tree, else recursively call insert. That shouldn't have fixed anything though. Yeah, no, it shouldn't. Why is I genuinely don't know why it's doing this. Let's just do prints. Let's just use some print statements, I guess, and see if I can figure out what's going on. Everyone's favorite print statements. So it printed 0 and 1. Why is it printing 0 and 1? Binary tree should be the first element of binary tree should be 10. Oh, but it prints left first. This is interesting. I will debug that later, purely because that shouldn't be happening. And I have a feeling that this is going to be some wonkiness. But this is correct, so my print statement's flawed. So I'll implement search, and then I'm going to copy this code into a Python file because I think it's Jupyter that's doing it, not Python. So let's just code the search function, and then we'll come back to that, guys, because I'm not wasting this entire tutorial on debugging a print function. So searching, since we have not a lot of time left anymore, searching is very much the exact same as inserting, like to the point where you could probably copy it and just do some basic changes. This is a short tutorial, so I can get away with doing it this way. So when you search for a value, you check, is self.root equivalent to the value? If it is, whoop-de-doo, you can return true because you found the value. If self.root is lesser than the value, that means the value is somewhere to the right. So if self.right is none, instead of setting a new value, what I should do is actually return false. I didn't find it. If my value should be to the right and there is nothing to the right, this is an issue. Else, I'm going to return whatever happens when I search to the right. And very much in the same fashion, if I were to go left and there is no left, then I return false. Else I return whatever happens when I attempt to search to the right. I'm going to copy this now into a Python file. Test.py. Bintree 10. And then let's grab this loop. And let's grab that data. I should do tree equals bintree 10. Oops. Print tree.root. So if I just print this here, it prints the number 10. If I print tree.left.root, the item immediately left of tree.left.root, not tree.root.left.root. That makes no sense. It's the number 4. If I call .left.left.root, it's 3. So yeah, it was an issue regarding some of the functions. So I should be able to bring my print statement back. So that was a Jupyter thing, and I have no idea why it did that. So let's make a print tree function that takes in self. And what we're going to do is if self.left is not none, that means that there's a number there or there is a bin tree there, and I should print, or I should call self.print tree on the left tree, whatever the left tree is. So self.left.print tree. That should be not equal. Very much in a similar way, if I want to print the right tree, I check if there is a tree to the right, and if so, I call my print tree on it. And all I'm going to do is between those, I'm going to print self.root with some space around it, and you can't add an integer and a string, so I'm going to cast it to a string. So if I call tree dot print tree, I should, in theory, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because when we print the left element first, the left element is always lesser, the middle element is always the middle element, and the right element is always bigger. So every item should be numerically sorted. If I wanted to print it in the order like this, where we print the roots, then its left child and its right child, I can run the code again. So we have 10, its left child being 4, his left child being 3, his left child being 2, his left child being 1 or 0. Then 0 had no left child, but he does have a right child of 1. 2 has no left or has no right child. 3 has no right child. 4 has no, or 4 does have a right child. 4 had 7 as its right child, which had 6 as its left child, 5 as his left child, blah, blah. It's complex to see it this way because it looks like there is no ordering. The ordering actually only really comes if you look at the binary tree fully drawn out. So let me pull up my tablet again, and I can show you exactly why this printing logic is the way it is. Where's my tablet? There's my tablet. So if you think about it, we're printing the left child first, then we're printing the root first, then the left child, and then the right child every time. Oops. So if I'm printing the root, I should print 10, then the left child, which is 4. However, we're recursively calling print, right? So I should print 4's left child before printing 10's right child. So I call 3, but I need to call 3's left child before calling 4's right child. So 2, and then 0. Then I call 0's left child, which is nothing, 0's right child, which is 1, and then I can work my way back up the tree. I worked my way all the way back up to 4, where I then finally can print his right child, which was 7. However, now I need to print 7's left children, 6 and 5, then 7's right children, 8 and 9, before I'm allowed to work my way back up to 10. Then 10 follows the exact same logic going right. Print statements like these are really hard to get your head around because you have to look at what's happening recursively. You can't just assume that when I type this, let me put it the way where it was sorted from small to great. If you look at it, left.printTree always happens before the print statement on self.root. No matter how I do it, I will always be printing the left item before printing my root item. Which means that when I print in the left item, I would print that left item's left item. It's a bit complex, but this is the dangers of recursion. I do not know, though, why. Oh, I have no clue what I just clicked, but Teams jumped in front of my mouse. I have no clue, though, why it's not okay to do printing like that in Jupyter. I don't know if it's a problem with the Visual Studio Jupyter or something like that, but apparently there's a issue when you try to print in Jupyter. The more you know. So at this point, it's down to questions, which never fun, because this is all the tutorial was. And if I didn't have that massive hiccup with the Jupyter Notebook, it probably would have been a lot smoother. This is why I genuinely hate Jupyter. We should be teaching everyone using straight up Python files. In fact, this course could genuinely improve if we were to rewrite the assignments as Python files and like give you a PDF of the questions and you just submit a Python file. I think it would be so much easier. But oh well. The Jupyter notebooks are pretty friendly. So yeah, if you guys have questions, ask your questions. If you guys don't have questions, you can always leave. If you guys have questions about the content or about different content, you can ask those here. It's just, this was what was on today's schedule.
Can I ask a question about assignment 5?
I see no reason why not.
I mean, I have some questions about my code, and I do not know why it causes an error. Can I share my screen?
If you have questions regarding why you got a wrong answer, those need to be addressed in office hours. Tutorial is not an appropriate place to do those. If you had a question about one of the questions, I could do that. But about your specific code, that's an office hour thing.
Oh, yeah. Thank you.
The only reason I say that is because tutorial is the time where it has to benefit everybody. If you have something that doesn't pertain to everybody, like only one person could benefit, then that has to be addressed in the appropriate manner. Nobody has any questions? So when you guys see this on the exam, you'll be fine?
Hi, may I ask when should we use binary like this? You just show us.
So, yeah, I can, hold on. Screen copy.
Yeah, because it seems like it is similar to like binary search.
Well, binary trees are what actually led to binary search as a concept. So binary search, if you think about binary search, I'm just gonna go down to a new line. Binary search is the concept where if you have a sorted list of data, like this, just the first 9 numbers, you start in the middle and ask, is that number bigger or smaller than your target? If it's smaller, go right. If it's bigger, go left. If you think about it, that logic is actually the binary tree's search logic. If the root is your value, you return true. If the root is smaller than your value, you look to the right. And if your root is bigger than the value, you look to the left. The binary tree directly led to binary search as a concept. The better thing, though, about straight up using binary trees is binary search can only ever work if the array you're looking at is completely sorted. In this specific tree, the array I was looking at was not sorted. However, it was still faster for me to use the binary search tree to find the number 14 than it was for me to use the array to find the number 14. Notice how I go through 9 items at the top, but only 4 items in the tree.
Oh, yes. So the binary tree search is used when the list is not sorted, but we can use binary search to for the list which is sorted, right?
Exactly.
Is that the logic?
Because if the list were sorted, the binary search tree would be lopsided. So
I see.
I'll just show you what happens. So let's say I wanted to build a binary search tree for the list of data. What's a good? I want something short because I don't want to spend the rest of this class just building a binary search tree. So let me Apologies. This is a very finicky software I use to record my tablet, so zoom in a bit so you guys can see it better. So if I pick the numbers 0, 1, 2, 3, 4, those are already sorted. If I wanted to search it, it would be better if I did, is it bigger than 2? Yes. Is it bigger than 3? Yes. Is it bigger than 4? Yes. There's nothing here. Return false. If I turn these numbers into a binary search tree, I insert 0, and I ask, is 0 bigger than 1? No. So I go right. I'm not going to be doing the fancy graphics. Then I insert 2, which goes like this. Then I insert 3, which goes like this. Then I insert 4, which goes like this. So if I'm looking for the number 4, in the binary search tree, I now have to do 1, 2, 3, 4 steps. But in the sorted array for binary search, I do 1, 2, 3 steps. So a binary search and a binary search tree have opposite use cases, if you think about it. The worst binary search tree you could make is on a sorted array, which is the only time you can use binary search. The best time for a binary search tree is as an unsorted array, because you can't use binary search on an unsorted array.
I see. Thank you.
No probs. Now, one cool thing is if you used binary search methodology. So if I just made a slightly bigger array, 1, 2, 3, 4, 5, 6, 7, 8, 9, it is extremely easy to turn a sorted array into a good binary search tree. And the way is, while performing binary search on a sorted array, make a tree on it. So if I start in the middle, let's say this is my middle. I think actually the middle should be 5, now that I think about it. But what you do is you would insert 5 into your tree, and then you would go left and right. What you do is you then take the left item, insert it to the left, and the right item, and insert it to the right. Then from those two items, you would go left, which would then insert 6, and you would go right, which would insert 8. And then from 2, you would go left and right to insert 1 and I'm running out of space, but 3. Then from those two items, you would search for the remaining children, which would add 0 to your list. It would add 4 to your list here, and it would add 9 to your list here. What you've done is by doing binary search, starting in the middle and going left and right, you've actually built a binary search tree in which is properly weighted. This is a weird case. I don't think you guys would ever use, like, if you already have sorted data, you almost never would use a binary, like you would almost never turn it into a binary search tree. There's no point. It is just faster to use binary search on the sorted data. But if you ever need to have sorted data become a binary search tree, that's how people do it. You start in the middle, choose the middle item as the root node, and then go left and right and recursively build more trees like that. Any other questions? going to sit here in silence for 10 minutes. I mean, if you guys are interested, I do have a version of the binary tree. I have this version, which actually uses the custom predicate function I was talking about earlier. So if I look at the test case, I made a function that takes in an x and y and returns if x is bigger than y. And what this does is it saves that function as a predicate variable and puts it inside every binary tree. When you go to insert, it then calls this predicate function, because remember, this is a function. It calls it on the root and the value. It's the exact same logic. However, if I run this file, again, this issue. I think it's just a moment. It's just an issue with the string function, in all honesty. So what I'm just going to do is I'm going to remove the string function, and I'm just going to add in the print self.left, print self.root. Oh, not print self.root, it's print tree. I should really use the if keyword, eh? Quickly rewrite that to match. Run the code. We call tree.printTree. So this prints it sorted from small to big. But what happens if I pass in a different function? Let's say I pass in a lambda function, but I check if y is bigger than x now, not x is bigger than y. Well, what this should do is instead of printing 1, 3, 4, 5, 6, 7, blah, 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 it should print the exact opposite, 17, 15, 13, 12, 10, 9, 8. Because now the left and right have been swapped. Additionally, I could do anything. I could do x mod y is equal to 0. So what this does is if x is divisible by y, then y will get inserted to the right. However, if it's not, it should get inserted to the left. I don't know if there's a case where this would happen, because 7 wouldn't be divisible by 5. 5's not divisible by 12. 12 would be divisible by 3, though, so that would diverge. 12 is also divisible by 6, so that would keep going right, which is divisible by 1, which is divisible by 4. 12 isn't divisible, though, by 9, so that would go to the left. Let's see if I can get some printing like this. Das left arrow. I want to just make it a bit clearer roughly where they are happening. So if I print this, as you can see, I have a bunch of left and right situations happening because one as a item is the most left. God, this is ugly. Hold on. End equals blah blah blah. There's got to be a better way to print binary trees. I just didn't want to look into it. Because you would never print binary trees like this. Only a madman would do that. Let's see what this does. Because I am a madman. There we go. So 1 has 7 to the left of it, has 5 to the right of it, which has some sort of weird situation going on. There's our root. Where's our root 7? There's our root 7, which to the right has 5, to the right has an empty node. This is a mess. Maybe what I'll look into is finding a better way to print these. It sucks that I can't print these because it's actually genuinely interesting to ask what would a binary tree look like if you printed everything using this rule. But this is the general idea for the code. I'm determined to identify if there's a way I can let's try if I do I've determined to get some sort of fun, fancy printer working. Come on, fun looking. No, why is that? Can only concatenate string, not none type to string. Oh, I'm not returning the string. Hold on. That actually kind of worked. Not the best, but so you can see 7 has a left of this, has a right of this, which has a right of this entire tree. 12 is divisible by 4, and 12 was also divisible by 6. However, 4 was not divisible by 6, so it's on the opposite side. 3 divides 6 evenly, so it's to the left of that. The entire thing is a mess, but it's actually kind of fun to look at. Not a success, but oh well. I'm just goofing around because no one's asked any questions. Like, I'm not gonna spend the entirety of the remainder of my tutorials in silence. So if you guys have to go, because you guys have class in 10 minutes, go right ahead. Because yeah, my tutorial time is up. I'm having fun, but it is time to go. You guys.